Welcome to Chapter 1, Tools for Analysis. We are using the text Advanced Calculus by Patrick M. Fitz, Patrick 2nd edition. Now, in this chapter, we would introduce you to a proper understanding of some fundamental properties of the set of real numbers and also explore some special properties of some of the subsets of the set of real numbers. And some of those subsets that we would be interested in would be the set of natural numbers, 1, 2, 3, and so on and so forth. 0 is not a natural number. Secondly, the set of integers. That would be negative numbers, 0, and positive numbers. So negative 2, negative 1, 0, 1, 2, 3. So that would be the set of integers. And thirdly, the set of rational numbers, Q. That is the set of elements that are of the form A divided by B, where A and B are integers and B cannot be 0. And lastly, we have the set of irrational numbers symbolized by QC. We say that for every real number x, x is an irrational number if and only if x is not a rational number. So examples of irrational numbers would include square root of 2, square root of 3, and at some point in this class, you would be expected to prove that if p is prime, then the square root of p is an irrational number. E is a very popular irrational number, and the most popular irrational number of all times is pi, and so on and so forth. I use this little diagram to illustrate the relationships between the various subsets of R. Here we have 0. We have the set of positive integers, the set of negative integers, and these three constitute the set of integers. Now, if I include fractions to that set, I get Q, the set of rational numbers. So the box in blue, that will be the set of rational numbers. Now, if I put on it the set of irrational numbers, all in black, then the box in blue and the box in black together would give me the big box that is in green, and that is the set of real numbers. So all of these are subsets of the set of real numbers. These are just some special subsets. The subset 1, 2, 3 is actually a subset of the set of R real numbers, but these are some very special subsets. Well, why do we have to end with R? Now, for this class, this is real analysis, advanced calculus, so we would mostly deal with real numbers, but just in case, if I add the number I, the imaginary number, which is the square root of negative 1, to R, then I get the box in orange, which is the set of complex numbers, numbers of the form A plus BI, where I is an imaginary number, and that equals the square root of negative 1. Well, we're not dealing with complex analysis today. We're dealing with real analysis, so we would concentrate our studies with R and the subsets of R. We would also explore some basic inequalities and algebraic identities. You must have heard of the triangle inequality, and so on and so forth. We would see those when we get there at some point in Chapter 1. Now let's get to section 1.1 that deals with supremum, infimum, mathematical induction, and completeness axiom. Definition 1.1. A set S of real numbers is said to be inductive, provided that, number 1, 1 is an element in S, and 2, whenever X is in S, X plus 1 is in S. If a set fulfills these characteristics, we say that S is an inductive set. It has the element 1, and if I pick any element at random from S, X plus 1 is also in S. You can quickly see that a set of natural numbers is an inductive set. It has the number 1. And if you pick any element from n, the set of natural numbers, that element plus 1 is also a natural number. So n is an inductive set. As a matter of fact, we would quickly see that n is a special inductive set. Another inductive set is the parent of all the subsets we just mentioned, and that is R. The set of real numbers is actually inductive also. Now, as I mentioned, the set of natural numbers is not just any ordinary inductive set. It is a particular inductive set. In fact, it is the intersection of all inductive subsets of R. So what are we saying about n, the set of natural numbers? Number one, the number 1 is in n, and 2, for every k in n, k plus 1 is also in n. The first two indicate that n is an inductive set, and the third one says if S is a subset of R and S is an inductive set, then the set of natural numbers is a subset of S. So n is a subset of every inductive subset of R. That is interesting. So if I were to index all the inductive subsets of R, and I is the indexing set, then the intersection of S alpha, where alpha is an element in I, is simply the set of natural numbers. So as infinite as the set of natural numbers is, it is the smallest inductive subset of R. That's interesting. Mind-boggling. Now let's move on to 1.2 and take a lemma. This class is theoretical and abstract and beautiful. So we would prove a lot of things. So here is our first lemma, and we would prove it. And I should just tell you up front, the proof is going to be very easy. Show that if A is a subset of the set of natural numbers and A is inductive, then A equals n. That's pretty straightforward. Now, since A is inductive by 3 above, n is a subset of A. Remember, we did say that if a subset is inductive, then the set of natural numbers is a subset of that set. So obviously, the set of natural numbers is a subset of A because A is inductive. Call that 1. Now, we are given that A is a subset of n. Call that 2. We do know that two sets are equal if and only if they are subsets of each other. That's how you define equality of sets. So by 1 and 2, we would say that equality holds, i.e. A equals n, and we're done with the proof. You see, some abstract proofs are beautiful and short. Okay, let's move on to 1.3 theorem, the principle of mathematical induction, PMI. Whenever I say PMI, I would always mean the principle of mathematical induction. The theorem says for every n in n, for every natural number n, let Sn be a mathematical assertion. Suppose that S1 is true. That means the statement is true when n equals 1. Also, suppose that whenever k is a natural number such that Sk is true, then Sk plus 1 is also true. So we suppose that Sk is true. And we can verify that Sk plus 1 is also true. If that is the case, then Sn, the mathematical assertion, is considered true for every natural number n. We call that the principle of mathematical induction. Let me break that down for us a little bit. Okay? So let the statement in question be denoted by Sn or Pn. I like writing it as Sn and Pn in this form. So there are 3 things we're going to do. Number 1, we have basis case. In this case, we verify that P1 or S1 is true, depending on whether you call the assertion P1 or S1. So you verify that P1 or S1 is true. Step number 2 is known as the induction hypothesis. Here you assume that Pk is true or Sk is true for some natural number k. You do not prove anything at the induction hypothesis step. you simply say assume that pk is true. Where k is a natural number, it has to be a natural number. And then we have the inductive step. This step is the most crucial of all the steps. Here you have to use the induction hypothesis to verify that pk plus 1 is true. If that holds, then you can say by PMI, your statement, your mathematical assertion Sn or Pn is true for every n. So we have the basis case, we have the induction hypothesis, and then we have the inductive step. I'll give you two examples. Use the principle of mathematical induction to prove that for a natural number n, summation j from 1 to n of j equals n into n plus 1 divided by 2, and summation j from 1 to n of j squared equals n into n plus 1 into 2n plus 1, all of that divided by 6, and hence find the formula for summation j from 1 to n j into j plus 1. Proof. Let Pn be the statement summation j from 1 to n of j equals n into n plus 1 over 2, and we remark that n is a natural number. So we start off with the basis case. We verify that P1 is true. What you do in such situations is to check the left-hand side and the right-hand side, and if they're equal, you say that P1 is true. As easy as that. So for the left-hand side, we go j from 1 to 1 because we are verifying the case when n is 1. So that will be j from 1 to 1 of j, and that is just 1. The right-hand side, again, n is 1, so that will be 1 into 1 plus 1 divided by 2, and that is 1. So the left-hand side equals the right-hand side, and therefore P1 is true, and step 1 is done. 1 down, 2 to go. Step 2, we assume that pk is true, i.e., that is very important. Always state the induction hypothesis. What does it mean? Okay, don't just end at assume pk is true. Always say that means, that is, write it down. So when you get to the inductive step, you can always refer back to that. Okay, so that is summation j from 1 to k of j equals k into k plus 1 over 2, where k is a natural number. Observe that for the induction hypothesis, we are simply replacing n with k because we are assuming that the statement is true for n equals k, i.e., we are assuming that pk is true. Now, we have to verify that pk plus 1 is true, i.e. the statement is true for n equals k plus 1. Again, you always say i.e. Write down what that means. It gives you an idea of where you're going, so when you get there, you would know that you've arrived. Okay? So, that means summation j from 1 to k plus 1 of j equals k plus 1 into k plus 2 divided by 2. This is where we are going. We're not there yet. We just stated where we want to go. Now we have to get there. And you start with the left-hand side and do not cheat. And break that down until you get the right-hand side. And you cannot do that without using the induction hypothesis. Very, very important. Okay, let's do that together. But summation j from 1 to k plus 1 of j equals summation j from 1 to k of j plus k plus 1. Now, this is a simple property of the summation sign sigma. I have simply taken off the k plus 1 term. So, summation j from 1 to k plus 1 of j, I take off the kth plus 1 term. So, I'm left with summation j from 1 to k of j plus the kth plus 1 term, which I have pulled out of the summation sign. And now I can apply my induction hypothesis since I know what summation j from 1 to k of j is. right here. This is what it is. So by the induction hypothesis, this first component here gives me k into k plus 1 over 2 plus k plus 1. I need a common denominator, so multiply top and bottom by 2, and I end up with this nice, beautiful expression, which my old friend algebra would break that down into k plus 1 times k plus 2 divided by 2, exactly what I am looking for. Therefore, I can conclude that pk plus 1 is true, and hence, by PMI, the principle of mathematical induction, Pn is true for every n in n. End of proof. Okay? The basis case, induction hypothesis, inductive step, you conclude. Let's try one more time. Let Sn be the statement summation j from 1 to n of j squared equals n into n plus 1 to n plus 1 divided by 6, where n is a natural number. Again, we start with the basis step. We show that S1 is true. The left-hand side, summation j from 1 to 1 of j squared is just 1 squared, and that's 1. The right-hand side, we replace n by 1. We end up with 1. So the left-hand side equals the right-hand side, and therefore we can conclude that S1 is true. Good. 1 down, 2 to go. Induction hypothesis, assume Sk is true, i.e., always say what that means because you would need it at some point. Inductive step, verify that Sk plus 1 is true, i.e., what does that mean? Again, always write it down so that you would know that you're done when you arrive at the solution. Otherwise, you might just keep going without knowing you're done. So it's a very good practice to always write down what the inductive step hopes to achieve. So, i.e., I want to prove that summation j from 1 to k plus 1 of j squared equals k plus 1, k plus 2, 2k plus 3 divided by 6. Again, this is just the i.e. Now we have to prove it. So we start with the left-hand side, and always remember to take off the k plus 1 term only. So this breaks down into j from 1 to k. Observe that the k plus 1 term has been removed from the summation sign. So this is just j from 1 to k of j squared plus the k plus 1 term, which is k plus 1 squared. By the induction hypothesis, we have it right here. Summation j from 1 to k of j squared equals all of this right here plus k plus 1 squared. I need a common denominator, so I multiply top and bottom by 6, and I employ my old friend algebra, and that breaks it down to k plus 1 into k plus 2 into 2k plus 3 divided by 6, exactly what I expected to get after I verify that Sk plus 1 is true. So therefore, I can conclude that Sk plus 1 is true, and by PMI, Sn is true for every n in n. Now the last part did ask me to come up with a formula for summation j from 1 to n of j into j plus 1. That wasn't a trick question. It was very direct. You just needed to know some of the properties of the summation sign. So summation j from 1 to n j times j plus 1 is the same as summation j from 1 to n of j squared plus j, and according to the properties of the summation sign, it distributes as summation j from 1 to n of j squared plus summation j from 1 to n of j. We already know what summation j from 1 to n of j squared is. It is n into n plus 1 into 2n plus 1 divided by 6, and summation j from 1 to n of j is n into n plus 1 divided by 2. And then employ your old friend algebra and come up with a nice, beautiful formula in the most reduced form possible, and you will be done. Beautiful. Next, we would look at proposition 1.4. It simply says, there is no rational number whose square equals 2. Or, to put it simply, the square root of 2 is an irrational number. The proof technique we would use here could be used to prove that the square root of 3, the square root of 5, or in general, the square root of a prime number p is irrational. Proof. You can use these properties of integers in the proof. Number 1, if x is a rational number, then there exist integers m and n not being equal to 0, and the GCD of m and n equals 1, such that x equals m over n. In other words, if I pick any rational number, I can always write the rational number in the form m over n, where n is not 0, and the greatest common divisor between m and n is 1. For example, pick a rational number 18 over 26. You can see that the greatest common divisor between 18 and 26 is not 1, but I can reduce this fraction down to 9 over 13, and the greatest common divisor is going to be 1. So, every rational number can be written in its most simplified form, where the greatest common divisor between the numerator and the denominator is 1. That property would be used in the proof of root 2, an element of QC. And secondly, if n is an integer and n squared is even, then n is even. Now, let me go ahead and prove the second one for us very quickly, using proof by contrapositive. I.e., we're going to assume that n is odd and then show that n squared is also odd. If you have forgotten proof by contradiction, proof by contrapositive, direct proofs, you should probably go back and review any text on elementary proof techniques. Now, assume n is odd. Then there exists an integer k such that n can be written in the form 2k plus 1, and n squared in that case would be 2k plus 1 all squared, and my little friend algebra breaks that down into 2k wiggle plus 1, where k wiggle is 2k squared plus 2k. So I have succeeded to write n squared in the form 2k wiggle plus 1, where k wiggle is an integer, and that means n squared is odd. Therefore, by contrapositive, n squared even implies n even. Now, for those who may have forgotten, n even means there exists an integer k such that n can be written in the form n equals 2k. N odd means there is an integer k such that n equals 2k plus 1, or you could also use 2k minus 1. Now, use these two properties right here and prove that root 2 is an irrational number. We shall look at it some more in class, and if you are watching this on YouTube and you need help with it, just leave me a comment and I will send you the proof. 1.5 definition. A non-empty set S of real numbers is said to be bounded above, provided there is a number C such that X is less than or equal to C for every X in S. And we call C an upper bound for S. C may or may not be in S. For example, take the set S equals closed at -5, open at 7. And let our C be 7. Then you would observe that for every X in S, X is less than or equal to 7. So 7 is an upper bound for this set S. So yes, S is bounded above. In particular, I want you to observe that 7 is not even an element of that set. As a matter of fact, for the set S, 8 is also an upper bound. 5,000 is also an upper bound. So there are infinitely many upper bounds if a set is bounded above. So we would definitely be interested in a particular upper bound. We'll come to that later. Look at another set. Just pick a finite set, -8, -7, 0, 1, 2, up to 8. Let's see equals 8. Then we see that x is less than or equal to 8 for every x in S. So this set is bounded above, and 8 is an upper bound, and in this case 8 is an element in the set. Number 3, look at this set. S equals the set open at -8 and infinity. Is S bounded? Is it bounded above? Can you find an upper bound for S? Why not? 1.6, the completeness axiom. Suppose that S is a non-empty set of real numbers that is bounded above. Then, among the set of upper bounds for S, there is a smallest or least upper bound, which is denoted by sup of S, or the supremum of S, or the least upper bound LUB of S. So like I mentioned, for the set S closed at -5 and open at 7, 7, 8, 9, 10, 5 million, and so on and so forth are all upper bounds of S. In fact, there are infinitely many upper bounds of S. So we're interested in one particular upper bound, and that is the least upper bound of S, or the supremum of S, or sup S. In this case, sup S is 7. So the supremum doesn't necessarily have to be an element in S, but it could be. If it is an element in S, then it is the maximum element in S. Interesting. I'm seeing so many things here. So we have the upper bound, we have the supremum, and we have the maximum. The maximum is the largest element in the set. And some sets do not have maximums. For example, the set S doesn't have a maximum, but it has a supremum. Interesting. Let's look at this proposition. Let C be a positive number. Then there is a unique positive number whose square is C, i.e. there exists X in R such that X squared equals C, and X in particular is greater than 0. Interesting. Observe that there are two things here: existence and uniqueness. You have to prove both. Now, an outline of the existence part of this proposition is found in exercise 17, page 11 of our text, Advanced Calculus, 2nd edition by P.M. Fitzpatrick. So we would verify uniqueness. Suppose there exists x1, x2 in R. Both x1 and x2 are positive, such that x1 squared equals C and x2 squared equals C. Then what we are saying is that x1 squared equals C equals x2 squared, and equal things are always equal, so that means x1 squared equals x2 squared, and that means x1 squared minus x2 squared equals 0, and simple factorization would give me x1 minus x2 into x1 plus x2 equals 0. Now x1 is positive, x2 is positive, and the sum of two positive numbers is positive. Therefore, x1 minus x2 must equal 0. And that simply implies that x1 equals x2, and therefore uniqueness is proved. 1.8 definition, we've talked about upper bounds. What about lower bounds? A non-empty set S of real numbers is said to be bounded below, provided that there is a number B such that B is less than or equal to X for every X in S. B is called a lower bound for S. B may or may not be in S. Oh, by the way, this is B and not C. That is the problem with copy and paste. So B may or may not be in S. The set S is said to be bounded if it is both bounded below and bounded above. Okay, skip the theorem. Let's look at this. Let's take S to be the set that is open at -8. You can see that this set is bounded above. 500 is an upper bound for this set. This set is bounded below. -5,000 is a lower bound for this set. So S is said to be bounded. Now, again, we're not just interested in any upper bound or any lower bound. We're interested in particular upper bounds known as the sup. So the sup for this set would be 8. What about lower bounds? Let's get to this theorem. Suppose that S is a non-empty set of real numbers that is bounded below, then among the set of lower bounds for S, there is a largest or greatest lower bound. And this is denoted by inf S or infimum of S or GLB, greatest lower bound of S. So for this set in particular, the greatest lower bound or the inf of S or the infimum of S is -8. You can see that this set has no minimum element. The minimum element would be the smallest number in the set. So a set could have maximum, minimum, supremum, infimum. So which sets in particular would have all 4? This set has only 2. It has infimum and supremum. No maximum, no minimum. What can I do to S to make it have all 4? Example 2. Consider the set -infinity to 8 is open at 8. Is this set bounded above? If it is, what is the supremum? Is it bounded below? If it is, what's the infimum? Is it a bounded set at all? What stops it from being bounded if it is not bounded? Now, what do you think is the relationship between union, intersection, complement of sets with boundedness? Can we say that the union or the intersection of sets that are unbounded can be bounded? Can I have a set that is not bounded above, not bounded below, another set not bounded above, not bounded below? Can I intersect those two sets and get a bounded set? How would the minimum, maximum, infimum, supremum look like? These are all very exciting concepts which you should start playing with. And remember, we are still looking at some tools for analysis. We haven't started real analysis yet. We're just looking at some tools that we would use. And so some of the tools we have seen here are the idea of boundedness, the completeness axiom, infimum, supremum. We've also seen the tool known as mathematical induction. In lectures 2 and 3, we would introduce you to section 1.2 that deals with the distribution of the set of integers and the set of rational numbers. And in section 1.3, we would deal with some inequalities and identities, and then get into chapter 2, where we would start with convergence of sequences, and that would be the beginning of real analysis, advanced calculus. Thank you, and God bless you.